Welcome to the ICPR 2020 virtual conference. I am Ram Muhammad Ubar presenting my paper Deep Iterative Residual Convolutional Network for Single Image Super Resolution with co-authors Luca Foresti and Christian Magnoli. The goal of single image super resolution is to recover the high resolution image from its low resolution counterpart. Usually SISR is described as a linear forward observation model by the following image degradation process, where the LR image is made up by convolving the latent HR image with the downsampling operator, usually bicubic, and further Gaussian noise is added into the image. The SISR is a highly ill-posed inverse problem, meaning that there could exist multiple possible HR images, resulting in a same downsampled LR image. So the regularization is required in order to select the most plausible one. By referencing the image observation model, the recovery of X from Y mostly relies on the variation approach for combining the observation and prior knowledge, and is given by the following objective function, where the first term corresponds to the data fidelity term that measures the proximity of the solution to the observation, and the second term is the regularizer term that corresponds to the image prior. The objective function g of x is too complicated to manipulate, that is convex and possibly non-differentiable function. So we use majorization and minimization framework to get the required solution. In framework, the function g of x takes the form as a q of x by the following two conditions. This means that q of x is the majorizer of g of x at the fixed point xk. So instead of minimizing the actual objective function g of x, we minimize the majorizer q of x to produce the next solution estimate. Therefore, iteratively minimizing the q of x also decreases the actual objective function g of x. Thus, we rewrite the quadratic majorizer for the complete objective function as given here. To start some an initial estimate x naught, we have a q of r, which is the distance function between x and x naught. In order to get a valid majorizer function q, we need to satisfy above two conditions. This suggests that G must be a positive definite matrix which holds if alpha is greater than L2 norm of H transpose H. Based on above discussion, we can rewrite the oval R majorizer as the following form, where Z is equal to the sum initial estimate x naught and the gradient of the data fidelity term. Finally, we proceed the optimization scheme to iteratively minimize the quadratic majorizer q of x by the following formulation as given here, where zk corresponds to that term and prox is correspond to the proximal operator, which is defined as. This formulation is treated as the objective function for the denoising problem, where z is the noisy observation with noise level sigma. In this way, we heavily relies on deploying the deep denoising network to get the required estimate by unrolling scheme as a k-finite step. The visual structure of our proposed SR strategy is shown here. We are initially given the LR image y and initial estimate x naught. Each network stage, that is ERD, produces a new estimate from the previous one. A single optimizer is used for all network stages with shared structures and parametered by finite k step. The L1 loss is used during training, which is defined as. The visual structure of ERD block is shown here. This part is correspond to the regularizer learning term, and project layer correspond to the proximal map, and finally clipping layer is used to clip the value between 0 and 255. For the quantitative result comparison, we compare our method with other state-of-art network at the scaling factor 2, 3, and 4 on the standard test benchmark dataset. Our results exhibits improvement in PSNR SSIM compared to the other methods except the EDSR. Since the EDSR has deeper network containing 16 residual blocks with 1.5 million parameters, while our model contains 5 residual blocks with 380k parameters. The visual results comparison is shown here at the scaling factor 4x. Our proposed method successfully reconstructs the good texture region, sharp edges, and finer detail of SR image compared to the other method. So our proposed solution follows the image observation physical model. We solve the SISR problem in an iterative manner by minimizing the discriminative loss function with residual learning. Our proposed solution exploits the powerful image regularization and large-scale optimization technique for image restoration. We achieve good PSNR SSIM with few trainable parameters, which is suitable for limited memory storage and CPU power requirement for mobile embedded deployment. Thank you for listening.